What we're going to do today is take a look at the frequency components of a guitar string that was plucked. And so I had this old guitar, and what I did is I plucked a string on it and I recorded it with a portable digital TASCAM recorder, which saves that as an audio wave file, which wave does not compress anything. It keeps all the information. The sample rate was 44,100 samples per second. So what I did is I brought that into Audacity and adjusted the amplitude so it's a full amplitude, and I can play it right here. That's what it sounds like. Now, I don't believe this guitar is tuned. Play it again. So that's what it sounds like. I think this was a low E string, which I read online is supposed to be somewhere around 83 hertz. But what we're going to do is we have this MATLAB script that I wrote. It does a bunch of things, but I won't go through every detail. But basically here I set up the sample rate and a few other things. And this is the one of the important lines here. This is where we use MATLAB's audio read function. And I have specified the location where this wave file is. And I'm going to name it ST, and SR is the sample rate. So later on, I go down here, and what I'm going to do is I'm just going to take 44,100 samples of that, a 1 second piece of that particular file. And then the next line, I use the FFT function. I'm taking converting from time domain to frequency domain. Basically, I'm taking the FFT of the time domain file, and now I'm adjusting it so it shows up in dB, because this will be easier to look at once we plot it. And then I'm going to plot it here, and I'm only going to do up to 2,000 hertz because I took a 44,100 sample chunk of this data. So 1 second of it, each bin is going to come out to 1 hertz when I do that. But I'm only going to plot out to about 2,000 hertz. And so if I go ahead and run this, and then later on I do a few other things that are unrelated. If I go ahead and run this, it's going to generate some plots. We're not going to talk about that right now, but we want to talk about this plot. So this is the FFT plot. On your bottom axis here, you have frequency, or pretty close to it. And this is the scale in dB relative to full scale. This is just 1/2 of the FFT. So technically, all of these values need to be upped by 6 dB. But we're not going to worry about that right now in this video. So when I put my cursor right on some of these points, X is 101. Now in reality, you've got to subtract 1 the way MATLAB deals with FFT. So that would be 100 hertz. This guitar is grossly out of tune, or possibly I plucked a different string. But you'll notice that the spacing of many of these is pretty uniform. So those are harmonics. So this being our fundamental, over here we've got something at about 200 hertz, which is roughly double the 100. That would be our second harmonic. And then over here we've got 300, 400, 500, 600. And if you keep going, you're going to find out that all these tones that are equally spaced, those are the harmonics. And all of those play into making the sound of that string. So when somebody says a guitar string is 83 hertz, or in this case it's 100, it's not just a 100 hertz tone. There's a whole bunch of other frequencies in there that make up the particular sound of that waveform. And it's not just the frequencies, it's the phase relationships of them. This is an FFT magnitude plot, so we're not looking at any of the phase, but there's a good chance that many of these different frequency values here have different phase with respect to each other. And then all of these other signals down here, they do also contribute to the sound of that particular waveform. But this is the main thing we wanted to show here is that that sound of that guitar string is rather complicated. It has all these different components that go into making it up. So it's not just a simple sine wave. You will find very few things in nature are a pure sine wave, like strings when you pluck them. They're always going to have additional frequency components that make them have their unique sound. And this would apply to pretty much any musical instrument. If you hit a particular piano key, you're going to see a similar kind of a plot. Won't be identical, but it's going to have harmonics that very well stand out, and it'll have all these other smaller but unimportant or not unimportant contributors. I should say important contributors that make up the final sound.